Hi everyone, my name is Soborno Bari from NYU's Quoron Institute, and today I'm going to review homomorphism. What is homomorphism? Well, it's a function from one surface to another that is bijective and continuous. There we go, lecture done. But if you haven't taken a course concerning functions or analysis before, you probably have no idea what this means, and maybe a vague idea of what this means, but no concrete definition. So, let's get to work in making this more intuitive. Now, first, you'll see the famous example all the time of two homeomorphic objects. This is a donut, or a shape that is in 3D geometry often called a torus. So now, let's take one half of this little donut. So this is our torus, and we're going to make it like a little dimple right over here. So now we can sort of lengthen it out a little bit. When the other half of the donut, or the torus, serving as the mug handle, and then we can develop a little hole in the top of the mug. So there we go. But this seemed completely unintuitive. We just shifted around the whole thing like Play-Doh until it became another thing. So, what does it mean to be bijective and continuous? Well, to be bijective, you have to be a combo of both surjective and injective. But those things are hard to explain. Well, not hard to explain, but I'm teaching this for a general audience. So this essentially means that an inverse of the function exists. Now, what is it I speak of when I say inverse? Well, essentially, imagine it like this. We have y equals x squared, or, better yet, f of x equals x squared. So now, what would be the inverse of f? Well, we want this to be true. So, that means this must be true. And for that to be true, then all we have to do is let f minus 1 of x be equal to the square root of x. The positive root, by the way. So, technically, we'd add these little bars. So, that is how we are going to signify the inverse. So now this inverse must exist, and it must be completely continuous. Now, what does it mean for a function to be continuous? Well, it essentially means there are no jumps, which basically states that if we have f of x comma f of x right here, and then we have x plus h comma f of x plus h right here. As h approaches 0, f of x plus h should approach 0. But it doesn't in something like this, like what we call the Heaviside step function, or the floor function, for example. The floor function looks like this, like a little staircase. And these little jumps are going to make it discontinuous. Something else discontinuous are functions like x squared minus 4 over x minus 2, where we get what we call removable discontinuities. You may recognize that this is just x plus 2 in fancy clothing, but actually, the consequences of there being an x minus 2 in the denominator is that at exactly x equals 2, so right around here, there is a little hole in the function, and that is a discontinuity as well, although that definition rarely gets applied to topology. It's mostly the whole jumping thing. So now, this seems to apply to every function you could think of. Even sine and cosine, the weird trigonometric looking functions, have a bijective and continuous inverse, and a very well known as well, the arc functions. Arc cosine, arc sine, arc tan. They go on. So, let's talk about something that is continuous. Well, no, it's not continuous. So, the thing about it is that it is, how do I describe this? It is bijective, but it is not continuous. So that is going to be the function from the regular circle with a radius of 1 denoted as S1 most of the time, and the interval 0 to 2 pi on the regular plane. Technically, we use a parenthesis here because on the sphere, 0 and 2 pi represent the same point. So 2 pi itself is kind of subtracted from the interval. So what I'm going to do is actually the 0 to 2 pi S1 mapped to 0 to 2 pi in itself is discontinuous, but I'm going to do something a little easier to explain and shift it over by pi over 2. So now, how do we map this to that? Well, obviously there are the same amount of points, as this has a length 2 pi, and this has circumference 2 pi. So everything matches up there. It's 1 to 1, which is part of the requirement for a bijective function. One to 1. And F inverse must also exist. So, what is the map from here to there? Well, that's going to be sine of theta minus pi over 2 cosine theta minus pi over 2. As you can see, very simple. So that's just going to map right here. This one is going to map right here, so on and so forth. But the real problem arises when we try to go backwards. What happens when we try to map the circle back to this interval? Well, this point goes right here at pi over 2. But the point right before it goes to 5 pi over 2. So there must have been a really drastic jump right in between in order to make this happen. So that's where discontinuity arises. Still, ridiculous things like the torus turning into the coffee mug are often technically homeomorphisms because of how lax this definition is. Then again, it's not a real policy or anything. It doesn't need to get more strict. It's just a mathematical concept, and it's useful as